Welcome back, everyone. So, for the main seminar, we have once again our very own Akhila, who will be talking about graph models for keeping the suspense a bit. Quantum weighted projective spaces. Take it away.
Thank you. Thank you for the introduction. So, as we just saw, I'll be speaking about constructing graph models for quantum weighted projective spaces. And this is a joint work with Aaron Kettner, who you might know. And yes, so classically, weighted projective spaces are defined as homogeneous spaces of or dimensional sphere with a weighted circle action. And quantum weighted projective spaces are also defined in a similar way. So we have the quantum spheres, which are defined as quantum homogeneous spaces of OQ of SUN, considered by Waxman and Soibelman, and they can be described in terms of generators and relations as follows. Which I would denote by OQ of 2n plus 1 is generated by Zi n plus 1 and their adjoints such that it satisfies a bunch of relations, including Z1 star plus etc. plus Zn plus 1, Zn plus 1 star equals to 1, and then Zj equals q to the minus 1, Zj Zi, for 1 less than equal to I less than or equal to j less than equals to plus 1, and then a few more commutation relations. And this star algebra admits a C-star completion, which I will denote by C of SQ of 2n plus 1. So now we have the quantum sphere, and we can now define an action of the circle here. So first choose L in n to the n plus 1. So this is what I will call a weight vector. So this is just n plus 1 many positive integers. And using this, I can define a weighted action, define a U1 action on the sphere by, so I can define it on the generators. So alpha t of Zi is just going to be t to the Li Zi. So if we were considering projective spaces, we will just take these integers, all of these to be 1. And then this is the usual action that we define on the quantum sphere to get the normal projective space, quantum projective space. And here we are weighting the action. So we introduce this weight vector, and then we define a weighted action. And we can consider the fixed point algebra of this action. Consider the fixed point subalgebra, which I would denote by P of L. And this is just elements in the odd-dimensional sphere such that alpha T of A is equal to A for T of V.
This OQ is just algebra.
Yes, no, just a star algebra.
Just star algebra.
Yes.
But the action just projection.
Yes. I mean, you can also define this at the level of C-star algebras, I think. So this is a universal C-star algebra given by, if you can just think of, if you don't care much about the algebra going on behind, you can just think of them as a C-star algebra generated by these elements satisfying these relations, and then define an action as the action on a C-star algebra, and then take the exponents of algebra. Just at the, yes. Yes, exactly. Thank you. So, and so OQ of this guy, this fixed point subalgebra, is called the coordinate algebra of quantum weighted projective space. And now we are inside the quantum sphere. This is the subalgebra of the quantum sphere. And so we can take the completion of this guy inside the sphere. So CQ of P of L is the C-star completion of OQ of P of L inside the quantum sphere. So this was, I think, first considered by Brzezinski and Fairfax, I think, and they looked at what is called quantum teardrops, which is just n equals to 1. If you put n equals to 1, then you get 2 generators. And they considered what they called a quantum teardrop. And then they also later considered multidimensional teardrops. And I think it was Andrea Landi who considered with all different weight vectors and introduced. This is from Andrea Landi. Okay, and we also know the generators for this algebra. So a set of generators for is generated by, first we have the obvious ones, which is just Zi star Zi with I equals to 1 to n plus 1, because if you take the adjoint and some element and it's adjoint, then it is, this is something in U1. So this is anyway going to be invariant. And the next and the other set would be Z to the K, which is Z1 to the K1, Zn plus 1 to the Kn plus 1, such that L1 K1 plus etc. plus Ln plus 1 Kn plus 1 equals to 0. And if you look how we define the action, then you can say that this is just the product of these elements. And if you just plug in this element into the action that we defined, then this is exactly the condition that we need to make these elements invariant. So these elements are invariant under the action, so it belongs to here. And in fact, this is generated by these elements. So we now have our C-star algebra, and we know the generators, and this is the C-star algebra that we want to realize as graph C-star algebra. And just so that we are in the same page, let me quickly tell you what graph C-star algebra is. So if you take E a directed graph, then C star E is the universal C star algebra generated by mutually orthogonal projections. PV such that V and partial isometries SE1 such that they satisfy SE star, SE equals P of R, the range projection, and then source of E is just this guy, and EV equals summation E in S inverse of V. So you can think of it as if you have a directed graph, then for each vertex you associate a projection, and to each edge you associate a partial isometry such that it satisfies these relations. So that gives you a C-star algebra. And so our goal is to realize these C-star algebras as graph C-star algebras. And similar work in this direction was done earlier by Szymanski. And what they actually did was they realized quantum spheres and quantum projective spaces as graph C-star algebras. And if you are interested, this is S3. This is the graph of S3. And this is just CP Q1. And I should really draw some arrows. And then also Brzezinski and Szymanski, they looked at weighted projective lines, quantum weighted projective lines. Which is the same thing that we consider, but just with n equals to 1. So you have just 2 weight vectors. And in this case, they showed that the graph is going to look something like this. So if I call this V1, then I have VL2 tilde, where L2 tilde is just L2 by GCD of L1, L2. So they realized these guys as graph C-star algebras, and this is the graph. And more relevant to us is the work of Brzezinski, Kramer, and Strong. They realized quantum flat manifolds as graph C-star algebras. So this, you can think of it as a class that contains Grassmannians and projective spaces and Wolfrags. I'm not going to explain what this is, but yeah, just to give an example, this is Grassmannian 4-2. And we are more interested in their approach because when Szymanski realized this as graph C-star algebras, they kind of guessed the graph and then constructed an explicit isomorphism. And then from there, they looked at the fixed point algebra under the gauge action and they got the graph of this guy. And they were also doing something similar, not with explicit isomorphism, but they went through length spaces. That is something else. But yeah, but we wanted to do, but that is a bit difficult. So we didn't want to do that. So we want to take their approach and how they realized so their approach was, yes.
Right.
Yes, yes. Thank you. Everywhere there is infinitely many edges. Yes. So their approach was relying on a result by Eilers Ruiz Sorensen. So I'll just state the theorem in a way that it is easy to state, and yeah, I will hide the rest. So this is by Eilers Ruiz, Hitsura, and Tom Ford.
It's that concept, the last one. Can you just a little bit explain?
Yes. Can I do that after stating the theorem? Because I think I think that would be easier. Yes. Yes.
Can you move the camera?
Sister algebra with yes. Smooth system algebra orthograph. So this is the theorem, and in our case, and also the case that they were considering, we can actually reduce this again. Our C-star algebra satisfy a little bit more hypothesis, which I don't want to get into. But in the end, what actually happens is that we can construct the graph by looking at the primitive ideal space. So in this way, the vertices of the underlying graph are going to be given by irreducible representations. And edges are going to be given by, if I have two representations, pi1 and pi2, then there exists edge from pi1 to pi2 if kernel of pi2 is contained in kernel of pi1. So this is the information that we need. We need to know all the irreducible representations, and we need to know how the inclusion relations among the kernels. So coming back to your question, and now the irreducible representations of flat manifolds are known, and that is given by these Dingen diagrams. Like if you look at the reduced words, and which you should know, and if you look at the reduced words, and then that gives you the representations, and also their inclusion relation also kind of depend on that. So if you have two irreducible representation, then they correspond to two different words, and there is the one kernel of one is contained in the other if and only if one is a subword of the other. So yeah, that is how this comes from, basically. Yeah. Here, they had a different idea. They actually gave explicit isomorphism for these quantum spheres, and yeah, it is not clear how they came up with the graph in the first place, but yeah.
Are there also infinitely many edges in first one?
Here, no. No. Yeah. Yeah, and in our case, in each of these cases, the graph that we end up getting is going to be an amplified graph. And by an amplified graph, I mean that there are infinitely many edges. Yeah, just whenever there is an edge. So if I forget to write infinity at any point from now on, just assume that there exist infinitely many edges, because that is the case that we will be considering. So we have what we want. Now we know what we actually need to, what we want. We need to construct the irreducible representations of these guys, and then we need to see how the kernels behave. So now we start working towards that. So irreducible representations. So the good thing here is that we have the following result about C-star algebras. If B is a C-star subalgebra of a C-star algebra A, unit reciprocal. If, yes, and pi is an irreducible representation of B on a Hilbert space H, then there exists pi tilde, again, irreducible representation of A on K, which contains H. So this says that if whenever we have an irreducible representation of the subalgebra, we can extend it as an irreducible representation of the bigger algebra. So this gives us an idea where to look for, actually. We defined weighted projective spaces as subalgebras of the quantum spheres. So if we know the irreducible representations of the quantum spheres, we can restrict it. And this, in fact, tells us that all the irreducibles of our C-star algebra should come from there. And the good thing is that the irreducible representations of the quantum spheres is already well studied. So we have the following. So if I take irreducible representations of C++. So EK, if EK is an orthonormal basis of L2 of N naught, then I can define two operators. One I say SQ. EK is just minus Q to the 2K plus 1. EK plus 1. So this is a weighted shift. And then this guy is just Q to the K EK. And the first guy is a weighted shift, and this is just a diagonal operator. And given this, we have for M in psi n is an irreducible representation of 2n plus 1, where now I need to say what psi n actually do. So if I take the first one of the generators, the first one, Z1, then this is nothing but I have, this is going to be on L2 of N naught to the N. And what is this going to do? This is just the weighted shift in the first component and the nidality on the rest. And I have M many here. And Now, if I take Z2, then this is going to be, first I have DQ and then SQ. In the T. So if I put Zm, then this is just going to be so if you look here, if I take the Z1, then I have shift on the first component and then identity on the rest. And then when you go to the second one, you just push the shift to the second component and add the diagonal operator here. And when you go to Zm, now you have diagonal operators in the beginning and a shift in the end. And as one would expect with Zm plus 1, you just have these diagonal operators. And now we don't have any shift to move. So this is just 0 for k strictly greater than km plus 1. So this is all the irreducible representations of the quantum sphere, and we have n many of them. And if you just look at the operators that I defined here, SQ and DQ, just to give you an idea where these representations for the quantum sphere comes from, then if you know a little bit about the representations, irreducible representations of SU2, then you might notice that the infinite dimensional guy is given by SQ star, and T12 is just DQ star, and SQ. So this is the representation of SU2, and from this, you can, with SUN, you have a surjective star homomorphism into this guy. And that gives you, and composing with that surjection, you get all the representations of SUN. And the sphere being, again, a subalgebra of this guy, you can restrict these representations to get the representations of the sphere. So that is where all these things comes from. Basically, everything comes from here. Okay, just to give you an idea where these things come from. Yes. No, with this theorem, I'm considering A to be my quantum sphere, and my B is the C-star algebra that I want to look at the weighted projective space. Yes, yes. Yeah. No, it is not related to anything. I mean, if you're familiar with, I think this is something that most people might have seen. So it is just to give an idea. If you have not seen the representations of the odd-dimensional sphere itself, this would ring a bell, like for someone who has seen it. If you haven't seen it, then you can just treat them as given here.
But also research, how do you that all the representations is as psi m?
These are, in fact, a complete set of infinite dimensional representations for the quantum sphere. Yes. I mean, I'm hiding a little bit here. Like there is also a one-dimensional representation for the quantum sphere, and you also tensor with the one-dimensional representation. So, yeah, there is something else going on. But these are the representations that we care about, or at least that is important to us.
And in the top left, this theorem, what if, so A is a severable unital
Type 1 C-star algebra.
type 1.
Yeah. Yes.
So the B is going to be type 1. Is that what's going to happen? Or?
Yes. I mean, these quantum spheres itself is a type 1 C-star algebra. So any subalgebra is going to be type 1. So this is again. Yes. Yes. So is there any other questions? Yes, we are in the question mode. No? Okay. Okay, so we have the So we have the representations that we think might be the irreducible representations of our C-star algebra. But what happens is that now we do what we can do, which is restrict psi m to CQ of P of L. Now what happens is that this gives us a representation of our C-star algebra, but this is no longer irreducible. So if you restrict to a subalgebra, there is no need that is going to be irreducible, and that's exactly what is going to happen here. These are no longer irreducible, but what happens is that this is no longer irreducible, but it splits as a direct sum of irreducible representations. So now we want to see how these guys split. So, and okay, so we can think about it as if you are given a, suppose I have a shift operator, I take S2. Then if I want to say the splits as a direct sum, then I want to find invariant subspaces for this representation and see that, okay, if that is irreducible, and that in fact gives me a direct sum of irreducible representations, and that is what I'm interested in. So if I have a shift square, then what do you do? Acting on L2 of N naught, then if I just, this is the first thing, and if I act by S2, then it takes me here. And if I act again, then it takes me here, and these guys give me an invariant subspace, right? So we are using a similar idea here, but now we have a bunch of shift operators. And so if I take one of these generators, then we can see that Kn, Zm plus 1, Kn plus 1 is just going to be SQK1, DQK2. So if I apply this representation and to one of our generators, then this is what comes out of it. So this is just going to be a tensor product of shift operators with some diagonals. I only wrote the diagonal guy here, but there is going to be some DQ everywhere. But we don't care about those. I mean, also, we don't need to care much about the weight of the shift, but we are interested in how this shift operators moves the basis elements around. So I can just treat it as SK1 tensor, etc. tensor SKM plus 1, and then do what I did here. So now this is a bigger element, but we can just act this on basis element and then consider the cyclic subspaces generated by a single basis element and see what happens. And so this is the basic idea. And then what happens is that those cyclic subspaces, which is definitely invariant, are also going to be irreducible. So that is what is going to happen. And now I can write down the definition of these subspaces, but these and L, as I already told you, is the weight vector. And then I define Li tilde to be Li divided by GCDF. In that case, I can define Lg to be Kn So I'm not sure how much information you can get from this guy, but you can again think of them as cyclic subspaces. I think that would be a good way to think about it, and this is a way to write it down. Maybe not a very good one, but it is a way to write it down. So what happens is that these are going to be, then if you look at L2 of Lj, sitting inside L2 of n0 to the m, this is going to give me an invariant subspace. And psi mj, which I define to be this restricted to L2 of Lj, is irreducible. So, and another thing is that you can see that if I take j not equals to k, then I didn't say where j is from. J is 0 to lm is from 2 to the minus 1. If I take Lj and Li for I not equals to j, then these are going to be disjoint as one would expect. So this in fact gives me a direct sum decomposition of the representation. So we have the following result. Sin j such that j equals to 0 and then tilde minus 1 n equals to 1 to n is a complete set of irreducibles for CQ of P of A. If you have any questions about this, please feel free to ask now.
You take one of these, you see how many components it decomposes.
Yes, because it is this many. So yeah. Yeah, so you can, okay, if I have the spheres here, then I have psi 1, etc., psi n. And if I have C of P of L here, then psi 1. This is just the, okay. Here I have psi 1 if I have Ln, L1. Here I just have psi m1 many, and then here psi 1 1, etc. Psi L2 tilde many, and minus 1 psi tilde minus 1. So all of these guys just split. And this, if, I mean, I already told you that the graph is just going to be, in the graph, the vertices are going to be the irreducible representations. So if you just look at the case n equals to 1, then you can already see why here, and this makes sense here, because we said that in the first guy I have 1, and then in the second level I have, then you can think about it as if this is how the complex projective space look like. So you can think about it as this guy being split, getting split, the smaller vertex getting split into this many, and this agrees with what we have there. That would be a way to think about it.
But like this, the complete description.
Yes, 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 exactly. Okay, now we have all the representations, and now we need the inclusion relations and kernels. So for this, one observation that we can make is that if phi1 and phi2 are two representations of a C-star algebra, two reps of A, then if kernel of phi2 is contained in kernel of phi1, then I can define a map phi from image of phi2 to image of phi1 by just sending phi2 of A to phi1 of A, and this gives me a well-defined star homomorphism. Satisfies phi1 equals. So if I have two representations and if I have such an inclusion between their kernel, then I can define such a star homomorphism which satisfies this guy. And conversely, if the rex is phi such that phi1 equals phi composed with phi2, then the kernel of phi2 is contained in the kernel of phi1. So then I would get this. So this is what we want. So if we want to show that the kernel of, if I take two representations from here, and if I want to show that the kernel of one of them is contained in the other, then I can just construct such a star homomorphism between their images. But now the problem is that we don't know our C-star algebra well enough. I mean, we know the generators of the C-star algebra, but we don't have a complete set of relations like we have for the quantum spheres, for example. Like we know it is generated by these many elements, but we don't know what the relations are. I mean, we don't know what the relations are in our C-star algebra, and also we don't know how this would look like. We don't know what kind of relations there is in these images. So, which makes it a bit difficult. So our approach to this, or the way we wanted to look at it to solve this issue, was to look at a universal C-star algebra and such that it contains one of our images, and which allows us to define a star homomorphism. And as the pre-seminar happens before the seminar, you already know that that is going to be partial cross products. And so how do we do that? I'm going to be a bit fast here because you have already seen everything with this. So we can take let L be n naught to the m, and this is one of the LJs that we have seen here, and X is an ideal if P in X and P in L0 implies K plus X is in X. So it just means that if I take X being an ideal, just means that if I take any point, any element in X, and then I just add something from L0, then I just end up getting something in X itself. And from here, you can kind of see that L0 is kind of special because that is exactly the terms that appear in this shift. So if I take anything from L0, then those are and the corresponding shift is the guy that I get if I apply my generators. So with this, I can define DL to be C-star algebra generated by B into to the end. Where one is the projection into L2 of X sitting inside L2 of L. Now, as we have seen earlier, I mean, this was the kind of the similar example was seen in Aaron's talk towards the end, and there we defined an action of the integers, and here the group that I would be considering is, I can just take this to be such that there is skin plus 1 such that K1 plus etc. plus n plus 1 Kn plus 1 equals to 0. And this is the group that I will be acting with. So this is a group because this is a homogeneous equation and the solution, and this is the solution of the homogeneous equation, but okay, one element is missing, but this still forms a group, and we can define an action of this guy on DL as we have seen earlier, which allows me to construct the cross product PZ. Now we can embed this cross product into B of L2 of L by, I can represent this guy in B of L2 of L as we have seen earlier by defining a covariant representation. So for that I can define a map here, which is just the usual, because this guy is already sitting inside this guy, so this is just the inclusion. And then for U, I can map PZ to B of L2 of L by sending an element P to P Pn to Spn tensor, sending it to this shift operator. And this gives me a covariant representation. And in fact, this is going to give me an embedding of this cross product inside this guy. And now we have everything that we want to look at the inclusion relations. So for that, I would be considering psi ml and minus 1k. This is, we already showed the levels here. And so I'm taking some representation in one level and another representation in the level below. So if I take two such guys, then we know that one is going to be psi m is a rep on L2 of n naught to the m or L, and then psi minus 1k is in L2 of n naught to the m minus 1. So what would be a way to go from n naught to the m to n naught to the m minus 1? We can just delete the last component. So if I have km, then I just map it to k1, etc., km minus 1. So what happens here is that I have my C star algebra, and if I apply psi ml, then I have this guy, and this sits inside. I mean, I already told you that we can embed this into B of L2 of L, and this embedding is in such a way that it contains the image. You can see this because we already have these shift operators, and these are exactly the shift operators that appears somewhere. cannot see that anymore. But if you here, these are exactly the shift operators that appear here. And you can show that these diagonal operators are also going to be contained in this cross product. So in fact, you are embedding this cross product into B of L, 2 of L in such a way that it contains the image. And this is where we actually didn't. This is how we can get such a map without the explicit commutation relations. And now, here we have the K and image of pi m minus 1K. And this is something that sits inside. So if I take such an L subset of this guy, then I can delete the last component. And if I assume that this K appearing here is contained in row of L, then I have this, and I have a way of defining a mapping here by, again, a covariant representation by, I can take B of L and map it to by just taking this guy to row of X and U by taking PM to SP1. I just delete the last one. This is same as the other one, but now I don't look at the last guy. And this indeed gives me a covariant representation. And I have this map here. And if we restrict it to this image, then this gives me a map here. And this is the map I need for the image. And such that psi m minus 1K is equals to so here, I mean, I said that I'm assuming that K is sitting inside row of L. And what happens if it isn't? This tells me that, okay, I mean, we saw the definitions here. This is saying that if I chop off the last entry, then I get something in the lower level, in the upper level, depending on what you say. So if that doesn't happen, if this condition is not satisfied, then I don't have an edge. Then there is a way to show that I cannot have such a high star homomorphism from using some spectral, looking at the spectrum of these operators, which I'm not going into. But in the end, what we have is that the kernel of psi m L is contained in the kernel of psi m minus 1K if and only if K is contained in row of L. So if I have this condition, then I can do this, and then I would get a star homomorphism, and that tells me that the kernel is contained in the other one. And a way to, do you have any questions at this point? Okay, so if we are just given a weight vector, then usually to draw a graph, you don't want to go through the entire construction, I would guess. So we should be able to realize this just in terms of weight vector. And that is the following. And so now if I take the kernel of psi mj, as I defined here, now I'm considering all of this, is contained in the kernel of psi mi if and only if GCD of lm minus 1 tilde, lm tilde divides I minus 2. So you can express, it is possible to express this condition just in terms of the weight vector. So if I'm given a weight vector, then I can see if there is an edge or if the kernel of one representation is contained in the other just by looking at this condition. And this is a computation that you can see do in 10 seconds. So yeah, so basically you can draw the graph just by looking at the weight vector. And now to give you an example, if we look at 1, 2, 2, if I take a weight vector 1, 2, 2, then I would have one vertex here because L1 tilde is always going to be equals to 1 because I defined it to be L1 by GCD of all the guys up to there, which is just L1. So this is always going to be 1. So I have a 1 here. And then I would have GCD of 1 and 2 is just 1. So again, dividing 2 by 1, I get 2. And here also similarly 2. And I get an edge like this because this is my 0, this is my 1, this is my 0, this is my 1. And so what happens, and from here, what you should think of is that we don't have an edge everywhere. And this would have been an obvious guess in some sense. If you see that the vertices just splits, then an obvious guess would be, okay, then you have edges from everywhere, basically, edges between all the vertices, like to have these and yeah, everything. But that does not happen. And in fact, that can happen depending on, again, the GCD. If you have something that is just relatively prime, then you have edges everywhere, basically. And infinitely many edges everywhere. And from the graph, one can see that the C-star algebra only depends on this L tilde, like whatever I mean. It doesn't matter if I take two weight vectors, L and K, such that L tilde is going to be equals to K tilde, then they're both going to have the same graph. So these C-star algebras are going to be isomorphic. And actually, in their theorem with Eilers, Ruiz, Sorensen, they also prove that the C-star algebras are isomorphic only if the graphs are isomorphic. So this way we obtain a complete description of the C-star algebra. Like if you just look at two weight vectors and you can just compute this guy, and if they are not equal, then your C-star algebras are not isomorphic, and if they're equal, then that is isomorphic. And that is an information that we get from the graph. And by looking at the graph, again, we don't have any loops or anything. We have infinitely many edges. So these are going to be AF algebras, which is also not obvious otherwise. So this is all I wanted to tell you today. So thank you.
Questions for Akhila?
And now you have also one Q, CQ, and
Yes.
where is the wait,
Yes. Another thing that we get from the graph is that the C-star algebra does not depend on the Q.
okay, so it
Yeah.
is.
And
I
that
see.
is true for all of these guys. Like, yeah, the star algebras are not isomorphic, but if you just look at the C-star algebra and the C-star completion, then all of this is Q independent.
Okay, and
So-
also, what is the range of the Q?
From 0 to 1.
0 to
Q in 0, 1.
okay. So it doesn't matter to Q. Okay,
Yes.
thank you.
So just following up on the very last thing you said, so you detect isomorphism pure just from the graphs. So do you Is it obvious how many isomorphism classes there are if you consider like all of the weights? Like, are there infinitely many? Is that or I don't know.
Uh, I don't know. I mean, there should be, right? Because I mean, if I think about it, just I don't know. If I just look at, I don't know. I mean, this L tilde comes from dividing by the GCD, right? So if I just take one, P1, etc., and all prime numbers, then I cannot divide by. I mean, this is one isomorphism class, and I can have infinitely many of these isomorphism classes, right?
Right.
Taking just different prime numbers. So, yeah.
Cool. But were you saying that just those specific examples you drew were AF algebras, or is that a general fact?
That is a general fact.
Right. Okay.
Like this is how all of our graph are going to be look like. It is going to be layered graph with different layers. So if you are looking at, if you are looking at not CP but WPN weighted projective space where we have n+1 weights, that is going to be n+1 mini generators, then that is going to have n levels and which splits in this way, and everywhere there is going to be no loops at all. So if for a graph C-star algebra, if there is no loops, then that is going to be an AF algebra.
Okay, cool. Thank you.
That's it for two when you try to extend.
Yes. What goes wrong is actually with the irreducible representations. Here we are in a good position because we have the sum of shift operators. Like we have the shift operators here, and if you look at the Grassmannians, then now our generators are going to be quantum minors. So with that, you can have a sum here. So what I would get is that the image is not going to be just one of these, but two terms or three terms or whatever. I mean, for 2, I think 2 terms. Then you cannot just multiply. Then for the generators, you have to multiply them again. And it is not easy to look at the invariant subspaces. That is not easy. Yeah. Yeah. Mm.
Sorry.
Any this from the online audience?
Yeah, Akhila, these graphs look a little bit like truncated Bradley diagrams or something. Can you say what the AF algebras you get are? Like, are they related at all to, can you relate them to the AF Bradley diagrams?
Maybe you can, but I can't now, and that is not something that we have thought about. So
So you don't know what kind of AF algebras you get, for
No.
example. Okay.
Sorry.
Yep. Go ahead.
Hello. So I have only one question. The main result was a complete set of irreducible representations for this quantum space. So what do you mean by complete set?
Yes, by complete set, I mean that if you have an irreducible representation of the weighted projective space, then that is going to be one of them. So this is all of them. Like if you find any irreducible representation, it is going to be unitarily equivalent to one of these guys.
Oh, okay. Thanks.
Yeah, and a comment then. I mean, I probably told you this before and you already thought about it and told me why it was wrong, but I don't remember. So if you go from the A series to the B series, so you're looking at like SOA. Then the corresponding flag is of course cross, which means that basically your generators of the corresponding U1 bundle, which would be a sphere again. They're just matrix coefficients and the antipode matrix coefficient.
Mhm.
And the antipode matrix coefficient is again actually a matrix coefficient because of the B series, the antipode is quite easy.
Mhm.
So then maybe something like this work.
Something like,
that you have here, like you want here, just the
okay,
very
okay,
so that maybe if you go that the generators are much easier.
okay,
They're just big. They're in the same way here for the spheres. The generators are U by one
yes,
S and U J. That's what they are for the quadrics as well, for the first class in the B series.
okay,
Also for the C series, yeah.
okay,
Except it's even easier because the antipode, the star, does not give you, I mean, the antipode is a quantum microgravity.
Mhm.
In this case, it's easier because the antipode of the star is just a scalar multiple of the matrix coefficient again.
okay,
So that
Yeah.
might be an easier thing to do as well.
okay, yeah, yeah.
That's actually what I said. I mean, oh yeah, it's and nobody has that. I mean, even classically it is.
Okay,
Yeah, it's beautiful.
thank you.
Any final questions from here or online? If not, then let us thank Akhila again. And we'll be back next week, exceptionally on Wednesday, for Antonio's talk. See you then.